Hello, wonderful people. Welcome to Cosmology Talks. Today we have Cyril Creque-Sarbinowski, who is a Flatiron Research Fellow at the Center for Computational Astrophysics. He's talking today about cosmological models that might generate parity violation in the universe, specifically inflation models and Chern-Simons gravity, which I'm sure he'll explain in detail during the talk. This is interesting because, well, I guess hints of parity violation seem to be the most popular thing on this channel, and this is a theoretical model to achieve it. One shouldn't believe a model without data, but I also like the lesser known saying that one shouldn't believe data until one has a compelling model to explain it. So this sort of theoretical work is very important to deciding whether we believe these signals of parity violation are true or not. So I'm keen to hear about how well motivated the physics in the model is and whether there are any independent signatures one could look for to validate it. Welcome, Cyril. Do you want to start by telling us briefly about your paper?
Oh, well, thank you so much, Sean, for the introduction. So I think you've already mentioned some of the bits and aspects of it. But yes, the purpose of this paper, which is sort of highlighted here at the bottom, its purpose is to investigate whether gravity can yield an observable signature in the early universe through parity violation. And so the answer that we found to this is yes. So we can observe it potentially, and it does have a signal.
The way I understand it, this birefringent stuff is not what you're talking about, but the parity violation and correlation functions, the one that's potentially already been observed, is that something that this model can definitely be producing?
Yes, that would be the type of signature. So the observable of interest would be the galaxy trispectrum.
If people are remembering this talk 6 months, or your paper 6 months from now, and there are only two things that they're actually able to remember, what would you want those two things to be?
Yes, so the two things would be that gravity can imprint large and observable parity violating signals in cosmological correlators. And there are potential aspects of finding smoking gun signatures of baryogenesis in cosmological correlators.
All right, let's get into the background. Why are you doing this? Why is parity violation something we might suspect we might see? Why is Chern-Simons gravity an interesting thing to consider as a possible new physics model?
I would definitely say the beginning motivation for this investigation began with last year's pair of papers that came out around June of 2022 that showed hints of parity violation in the real space 4-point function of galaxies. And so when this came out, we were sort of interested in what type of models can give rise to this. And since I had some expertise in Chern-Simons gravity, I was like, possibly this type of model can give rise to it. And so, but as we worked through it more, we also saw that it was just interesting for a variety of other reasons besides just the hints of itself, because of the connections of a parity violation to baryogenesis as well.
Yeah, let's get into the details now then. What is the model? What is the signature? How does it relate to baryogenesis? That's quite exciting.
Yeah, okay. So I guess I can just go through the entire things, and I if I may, I'll sort of maybe give a couple of intro things, maybe, because I think it's nice to have a sort of broad picture before going to the weeds. The first of which is, what is parity, and, how can gravity violate it? Parity in 3 dimensions is most simply described by the flip of a signature of a 3 vector, so x goes to minus x. And when we speak of fields in 3 dimensions, parity splits them into one of 2 types. So you have parity even fields, which transform under the plus, and parity odd fields, which transform under the minus. When we speak of violation of parity, sort of the simplest way that we can look at parity violation is by looking at 2-dimensional shapes and how parity acts on them. So consider the disk and consider its mirror reflection. So in 2 dimensions, one must specify a axis with which to reflect over. But when you reflect disk across the mirror, get the disk, so it does not violate parity. But if you have something like a lightning bolt and you flip it across the line, then that is something that violates parity. When we speak of gravity violating parity, one needs to first be a bit more detailed. And so gravity is described at low energies by interactions between gravitons. And so gravitons are like photons, they're massless particles. And they have 2 helicities, a left and the right helicity, so counterclockwise and clockwise. And the thing about these helicities is that they're parity inverses of one another. And therefore, if you have them in equal amounts in the universe, you're going to have no parity violation. But if you have unequal amounts of left-handed and right-handed gravitons in the universe, then you have parity violation. And so a bit more specifically is that if you have a difference in the amplitudes, so A sub L and A sub R of these gravitons, then you'll have parity violation. And a bit more specifically, it's encapsulated in the parameter pi circ, which is the degree of gravitational circular polarization. And so it's just a difference of left and right-handed divided by the sum of the two. So it's between -1 and 1, depending on which handed. And the simplest model which gives rise to such a signature is Chern-Simons gravity. So in Chern-Simons gravity, you have, your metric G with Lorentzian signatures, hence the minus factor. You have some additional pseudoscalar called the DCS pseudoscalar. You have your standard Einstein-Hilbert term, and you have sort of the main bread and butter of Chern-Simons gravity, which is this last term. It has a coupling constant, 1 over F, called the DCS decay constant with units of energy, and it couples to what's called the Pontryagin eigenedensity, which is a particular contraction of the Riemann tensor with itself. In particular, it's a contraction that involves the Levi-Civita tensor epsilon mu nu alpha beta. And even at this level, you can sort of see where parity violation may arise, because when one takes x to minus x in the action, the way that it involves the Levi-Civita is that it ends up flipping two of the indices. And since Levi-Civita is a totally anti-symmetric tensor, when you flip them back, you pick up a minus sign. And since the pseudoscalar is a pseudoscalar, it also transforms with a minus sign. So that's how you can sort of already see that parity violation is going to be occurring with this term.
So it does need to be a pseudoscalar. Just an ordinary scalar would not violate parity here?
You would violate parity explicitly then, if it was a regular, which, one can entertain. Here we're just considering, in the most simplest cases, you want your action to conserve parity, but it violates parity in a specific sector. This term also spontaneously breaks, to be more specific and technical, it spontaneously breaks CP.
I see. But so at the moment, if I took S being the action, and I did a parity operation to all of the pieces of this, S would go to S.
S would go to S. No, it would not go to minus S. Yeah.
Yeah, okay. So the parity violation is coming dynamically rather than explicitly, as you said.
Yeah, exactly. It's not like the standard model where it explicitly and maximally violates parity. It's something more akin to like an axionic theory where you have an axion coupling to FF dual, where F is some field strength tensor of a gauge field. So this is Chern-Simons gravity, and so how does one observe parity violation in practice for us at least? And sort of the answer is galaxy endpoint functions. What are galaxy endpoint functions? So you have some statistical field delta G, which is the fractional deviation of the number of galaxies NG at some position X away from its mean n bar of G. And since it is a statistical quantity on three-dimensional space, it has a set of cumulants. So by definition, it has a one-point function, which is 0. So that contains no information. It has a two-point function, which is the variance. It's specified at 2 points, and due to translational and rotational invariance, one can take the 6 components of x1 and x2 and reduce it to just one component that is the magnitude of the difference between the positions. And in a similar way, you can generalize this to higher point endpoint functions just by concatenating more and more deltas along the way. However, not all deltas are useful for parity. The lowest order correlator that can encapsulate parity violation in an isotropic universe is the 4-point function. And sort of the way you can see this is that, well, let's consider first 2 points. So if I have 2 points right here and I do a parity flip, then, the fact that I have to do this continuously is going to give away the answer. But if I flip here, then I can do a rotation back if I have an isotropic universe and get the same result. So nothing happens if I have 2 points. If I instead have 3 points, you can sort of look at this series of pictures. So if I stick with this blue, purple, and orange diagram, and I do a parity flip, orange and purple swap, I can then do a rotation sort of across the diagonal like this and rotate back around and get the same exact picture as I did on the left. So since it's the same image, this can't capture any parity information. But if as soon as I add a 4th point, this green one, and I try and do the same trick, I parity flip and then rotate, I get the same image but with purple and green flipped, and there exists no rotation to bring these two to one another, and so the 4-point function does encapsulate parity violation. It's typically easier for a theorist to speak of the trispectrum, so it's Fourier conjugate, and in terms of the Fourier conjugate trispectrum, the parity odd trispectrum exactly corresponds to the imaginary part of the full trispectrum. Consequently, the parity even is the real part of the full trispectrum.
Okay, I'm being a bit stupid and naive here. If I have an XYZ axis and I push x to minus x, it's gone from a right-handed axis to a left-handed axis. What am I missing here?
So since orange and purple swap places, then now I can do a rotation of this object in this other way. So you've sort of like rotated out of the plane and back into the plane, and what you get is an image on the right. Now it's projected onto 2 dimensions, so it looks a bit funky, but this is what the third image represents. Once you sort of take this orange and you rotate out the plane and back into the plane. And then once you take that purple and orange, you rotate it back. So one thing, if you were thinking about this in full 3 dimensions instead of this projective 2D plane, essentially you'll go from something that looks like, I guess, like this to something that looks like this.
Let's say that the purple is my x-axis, orange is my y-axis, and blue is my z-axis. Then it is clearly right-handed. If I go from purple to yellow with my right hand, my thumb's pointing along the z-axis. After parity, it's clearly left-handed. If I go from purple to orange, I have to use my left hand. How can just rotations change the handedness of an axis?
The explicit construction is what's being shown. I think the thing that may be confusing is that the image you should be thinking of is like that it should be 3 points that are facing you with these 3 points. And then the other way it's going to happen is that it's going to be those same 3 points, but now with sort of looking like this. The 3 points are in the same positions, but the axes lines have now gone from being like in front of you to being behind you. That's the visual thing, but the thing is that if you actually consider these lines in addition, you're actually then secretly considering a 4-point function because you're considering the origin as well. And you shouldn't be thinking of the origin as a point inside of these transformations, just the 3 individual points in question. This is sort of the lowest order correlator that can encapsulate parity violation. The next thing that I want to say, since we want to talk to inflation, is like a little lightning review of inflation. And so what is inflation? It's a period of rapid acceleration in the early universe. The way it occurs is that I have some scalar field represented by this ball that sits at the top of its potential at some position phi naught. And it slowly rolls down this potential. And when it slowly rolls down, it accelerates the universe. And the slowness of the rolling is encapsulated by this parameter epsilon, which is the ratio of its kinetic energy, so its time derivative squared, divided by the rate of expansion of the universe squared, also with some reduced Planck mass. And the reason why inflation is so nice is because it solves 3 outstanding problems of cosmology: the horizon, flatness, and magnetic monopole problems. The horizon problem being the fact that when we look at different points on the sky, they are causally disconnected from one another. However, the CMB, as we observe, has a uniform temperature to 1 part in about a million or so. And so how do causally disconnected pieces have the same temperature? The flatness problem being the fact that the universe, as we observe along its spatial part, is completely flat. And the magnetic monopole problem being that gut theories often predict the existence of magnetic monopoles. However, we don't see any magnetic monopoles, so how does one get rid of them? The way that inflation gets solved these 3 problems is by essentially adding more time and also diluting anything. So the adding more time solves the horizon problem. You can imagine if you have 2 cars sort of in 1 point in space and they sort of go at constant velocity, then they'll hit 2 points right here. But if they're accelerating, they can go a farther distance away. And so if you have this initial period of acceleration, the expansion of the universe, you can then make things that were farther apart actually meet at a single point back in time. The flatness problem being that if you had any curvature initially in the universe, then really, if you always look close enough, it looks locally flat. So the Earth being a great example, it's a sphere, but when we look outside, for the most part, aside from maybe hills and whatnot, it's pretty locally flat. And so if you just take that small flatness and you expanded it out very, very quickly, you can get the entire universe. And the magnetic monopole problem being that if you produced any of these gut theory magnetic monopoles at high energies, like during inflation, they would be quickly diluted as inflation leads to volume increase of something on the order of e to the 180 or so. And so it's a huge dilution of any number density you initially had. And one great thing also about inflation is that its fluctuations indicated by these little arrows sort of seed the density perturbations for the growth of galaxies and structures as we see them today. Now, in the context of inflation, Chern-Simons has a little bit of a different story. So when we have the space-time metric, we expand it out to linear order in an FRW way with gravitons Hij The DCS pseudoscalar is then identified as the inflaton, and everything else stays the same. I've not written here the potential that's necessary for inflation. However, to get a sense of scales, since the inflaton is slowly rolling, you can take the potential to be constant. So say it has some scale to the fourth power. Then one can see from the Friedmann equations that if you have Hubble be about 10 to the 14 JeV or so, which is sort of an upper bound due to current observations, then this scale of this potential must be about 10 to the 16 JeV.
This metric you've written down, is that in full generality including vector and scalar perturbations, or is it only including tensor ones?
These are transverse and traceless tensor.
And I guess you didn't mention what this upper bound on H is. I guess it's from the current lack of detection of primordial gravitational waves via the CMB.
Yes, so since we do not see B modes in the CMB, that tells you that the tensor to scalar ratio needs to be less than about 0.04 or so, coupled with the fact that we measure the primordial amplitude for perturbations. Those two pieces together allow you to conclude that Hubble is less than about 10 to the 14 JeV.
Maybe now is a good time to ask a question I was going to ask at some point. So this Pontryagin density as a term you've added, is it the only term that comes in when you relax the symmetries by the amount you've relaxed them, or are there other terms that should be there as well?
No, it's not. It's not by no means unique. You can add higher order terms. You can also consider the Palatini formulation of gravity, where the connection and the metric are two independent quantities, and that as well is another way to go about getting parity violation. So what I spoke of is initially of having like amplitude birefringence. Essentially, when you have different amounts of left-handed and right-handed, you can also have velocity birefringence when the velocities of left-handed and right-handed components can move differently. And so that's encapsulated more by Palatini. There's also more modified gravity theories you can consider. These typically also have either some additional formulations, additional bits and pieces that make a richer phenomenology. However, here we were just taking sort of like the simplest approach.
And would the argument against there being a phi just r squared, just the Ricci scalar squared, be that would explicitly violate parity? The background to why I'm asking these questions is one might worry that why just this term, and if there are a whole bunch of other terms that should be there too, they might mess everything up in terms of have much stronger, less subtle effects, and therefore one's kind of putting a fine-tuning problem in by accident here, that one might need this term with a particular value of f, but all the kind of fundamental models that would have that term with that value of f would have a bunch of other terms that would just completely mess up all the observations. So you're setting all those other terms to zero. I mean, I'm not saying that therefore one shouldn't do this paper and this calculation and blah, 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 but just should we be aware that that might be going on, or are there reasons to believe why only this term would be added to this action?
It depends on how much things you want to relax. So the term you mentioned, something that looks like phi r squared, or r is the Ricci squared. If you still want parity violation to be encapsulated, then you have to explicitly violate parity. Now, again, standard model has maximal parity violation. So it's by no means something that needs to be sacred. You can remove it if you want. Here, again, it's if you want to conserve parity at the level of the action, this is the simplest term. Once you want to get rid of other things, then you have further other things you can consider. Okay, and so given this model now, one can just go explicitly compute the 4-point function. So I mentioned that we want to observe eventually galaxies, and that the inflaton's fluctuations lead to the seeds to galaxies. So what we're going to be calculating is essentially the 4-point correlation of these inflaton fluctuations. And so the next slide will be slightly busy, but I can go through it to mention. So here in the top left is the connected correlation of 4 inflaton perturbations at 4 different momentum values, k1 through k4. The contribution to this 4-point function or trispectrum is indicated by the diagram below it. So the solid line represents conformal time tau represented today, so tau equals 0 is today, while conformal time tau less than 0 is represented by anything below the line, so that's going back in time. For each pair of scalars, they interact with one graviton, represented by the wavy, wiggly line, and then interacts with the other pair of scalars. This interaction point here is, as you can see, an interaction between 2 scalars and 1 graviton, and it is not something you actually need to add in by hand or anything of that sort. It is naturally within any scalar theory when you perturb it linear order, which can be seen at the right-hand side. So if you just take the kinetic term of any scalar and you extend it out to first order with the perturbed FRW metric shown, then the linear term is a cubic interaction between the graviton and two inflaton pieces with contractions occurring between these derivatives. And so that's what these x's are. And even at this level, when we're looking just at this diagram, you can sort of guess how the answer should look like at the end. Because for each pair of inflaton perturbations is one primordial scalar power spectrum. And so since you have two of these pairs, you'll have two primordial power spectra. And since you have one graviton exchange in the middle, that's one graviton power spectra. So even right here, you can see what's there. Now, at this point, though, what I haven't mentioned are what are these, how did the momenta come in? And so the thing about this diagram that it sort of hides is that it's not actually one diagram, but three diagrams, similar to how in particle physics, when you have 2-to-2 scattering, you have an ST and U channel. The same thing happens in these correlators, where the ST and U channels are labeled by these ordered lists of vectors, K sub S, K sub T, and K sub U. And the way you should read it is that as I go from left to right in each of these lists, I am labeling the momentum of the inflaton perturbations in this diagram from left to right. And they're ordered in such a way such that the sum of the first two components is equal to the negative sum of the last two components, and that both of these are equal to the Mandelstam variable K sub I, which is the internal momentum carried by the graviton.
I think I followed everything you said, but just to kind of unpack it a little in case people are a little confused, I guess the difference is whether in your diagram where you've got two delta flies coming to the same vertex, whether that's K1 and K2 or K1 and K3 or K1 and K4. And then once you've got K1 and K2, the other two have to be K3 and K4. And once you've got K1 and K3, the other two have to be K2 and K4. So that gives you the three different things. And yeah, as you said, that's what you've got in KS, KT, and KU.
Precisely. Now, these four momenta are not just arbitrarily organized. They have some constraints due to translation invariance. And that constraint can be seen by this little diagram in the bottom right. So first I should explain my axes. So E1, E2, and E3 are all rotated versions of your X, Y, and Z axes. And they're rotated by the rotation matrix R sub I, where R sub I is defined so that E3, such that the Z axis gets rotated into the direction of the Mandelstam variable of K sub I. So it's a channel-dependent coordinate system. If I was looking at the S channel, then I would be looking at this picture with K sub S along the diagonal. If I was looking at some other channel, I would be using another coordinate system. But this is the coordinate system at hand, which is why you can see that the diagonal K sub I here lies along E3. And because translational invariance tells you that the sum of momentum is equal to 0, it's why it forms a closed quadrilateral here. And so this is sort of another way to represent a trispectrum in addition to this diagram on the left. Now, again, to go to galaxies, we're going to have to take a step. And so that step first gets taken by changing from the inflaton perturbations to the conserved co-moving curvature perturbation, because if you have different spots where the inflaton is a little bit larger or smaller, these fluctuations, they lead to pieces of curvature being a little bit larger or smaller. And where you have slightly more curvature is a little bit more of a gravitational potential, and that potential is what then leads to the growth of galaxies later. So later, in what follows, I'll just primarily be talking about this conserved co-moving curvature perturbation zeta rather than the inflaton perturbation. And they're just related by this relation right here with Hubble and the time derivative of the background inflaton. Now, we've done this calculation for the general sort of shape. However, it's to some extent with an asterisk involved, but it's most simply seen the answer in the collapsed limit. And so the collapsed limit is the limit where you take every momenta to be much larger than the internal momentum of the graviton. So what this tells you essentially is that the first two momentum are approximately equal and the last two momentum are approximately equal. And you have to take this limit in a particular channel. Now, when you do this, visually what happens is that you're essentially squashing the diagonal. So the term goes from the diagram I showed before, now shown on the left, to something along the right. And what we found is that in the collapsed limit, these scalar trispectra take a particularly simple form. So once again, the real and imaginary piece of a trispectrum correspond to the parity even and parity odd pieces, respectively.
Is that something you can explain why relatively simply, or?
I can give a one line, but Whether you believe me or not is another question, but the simple one proof is that the reality of the associated real space 4-point function tells you that the real and imaginary parts are parity even and parity odd. Because in real space, it has to be real. If I take the complex conjugate of the real space and I write it in terms of its Fourier conjugate, that's how those two pieces transform.
Where does parity come into this?
So if I take the 2-point function and I take a complex conjugate, k goes to minus k. Now, the prime here indicates that we're dropping momentum conserving delta functions. The sub C is the connected piece once again, and GE here indicates graviton exchange because we're only considering the contribution to the 4-point functions due to graviton exchange. Now, that being said, for the parity odd piece, so the imaginary piece, we are considering the leading order contribution. There's no other sources of parity violation in standard slow roll inflation. So this was the dominant contribution. And actually, even when you're talking about the real piece, it was shown in previous work that the graviton exchange is actually more dominant than the contact interaction for 3 inflaton perturbations. So in here, you can see the 2 copies of the scalar trispectrum, as I mentioned before. So here on the right, you can say K1 and K3. And so that's 2 copies. And then you have 1 copy of the graviton power spectrum, though it's not necessarily written like that because you have the tensor to the scalar ratio R here. And if you take R times any scalar power spectrum here, then you get a tensor power spectrum, which is a graviton power spectrum. So it's exactly the schematic form that we talked about earlier, with a little bit of additional bells and whistles of these angular factors. Theta here are the spherical coordinate system, where theta is the angle that deviates from the zenith. Now, chi is the angle, which takes a few more steps to explain. So I have 2 pairs of momenta that form a quadrilateral. If I consider each pair of these momenta independently, and they're not degenerate, then they each span a plane, and a plane is also defined by a normal vector. So if I take these 2 normal vectors and dot them together, they have an angle between them. Chi is that angle. And also, one thing that you can also see in the parity odd piece is that it actually is proportional to the degree of gravitational circular polarization as promised at the beginning. So there you see the signature of parity violation occurring even at this level.
R should also depend on Ki, right? Even in vanilla inflation, the tensor to scalar ratio depends on the scale you define it at.
In the simplest model, it maybe has some running, but at the simplest case, it's just a number.
I mean, it has a running, right?
But not very large, not a large running.
So what we're saying here is that the ratio of the tensor power spectrum and the scalar power spectrum doesn't change by enough over the range of K you're considering. Because if I consider from beginning of inflation to end of inflation, this changes by quite a substantial amount. It's not just 1%. But over, say, CMB scales, it doesn't change by much because the CMB is a very narrow range of scales.
Yeah.
Okay.
So R here, tensor to the scalar ratio, and it tells you that you have the graviton power spectrum. Okay, so one thing you may be interested in is what angular configurations maximize these shapes, and so that's what's sort of shown here in these 2 images at the bottom. The left being the parity even, and the right being the parity odd. The way that you should be looking at these diagrams is as follows. So as each color scheme corresponds to the momentum label shown either to the left here or up here on the right-hand diagram. Now, the line style of the purple and yellow lines are rotations away from the green and red lines by the amount indicated by the circles underneath it. So if I have a line style that's dashed, then it's indicated by this pi over 2 rotation. And these angles are all this chi sub I angle I mentioned before. If I'm dealing with the dotted line, then it's by this angle of pi. And for the parity odd case, instead it's pi over 4, 3 pi over 4, or 5 pi over 4, whatnot. And the fact that there are 3 angles here and 4 angles here is just because the fact that the 4th angle here is a rotation by 0, which I don't show explicitly, which represents the crossed rectangle. And the fact that there's this plus versus this kind of cross imagery is primarily because there's a cosine versus a sine in the parity even and odd. Now, one thing you may be seeing already is the fact that if I take the ratio of this parity even and odd parts, or actually the parity odd to parity even, I get a very simple result. It's just the degree of gravitational circular polarization times an angular factor. And this angular factor here is twice this angle I mentioned before. And this 2 here is no accident. It's actually the graviton spin. So if this was instead an exchange by a photon or some U1 gauge field instead, you would get something that's like a cotangent of a single Creque-Sarbinowski, but you would still have a degree of gravitational circular polarization. So this is sort of a nice thing because it's sort of a model independent way to sort of see what type of particle is being exchanged if you have access to both the parity and parity even and parity odd parts of a trispectrum.
Why? Because don't we just measure 2 times chi rather than 2? How do we measure chi separately so that we can tell whether it's cotangent of 2 chi?
Well, the way you do is you'd measure the trispectrum, you would measure its parity even odd parts, you would measure them in its particular collapse limit, and you would take the ratio of any momentum configurations, and you would just wiggle your 4 things like this, and if the rapidity of the angle goes by 2, you know it's a graviton. If you know it's by 1, it's a U1 field.
Wow. Yeah, that's cool.
Yeah, and so one thing also you may be seeing is that it's proportional, it's sort of in this standard case, proportional to the tensor to the scalar ratio R, which, as mentioned before, is limited by bicep to be, due to the non-observation of B modes, to be less than about 0.04 or so. And that's a small amount. So the sort of standard dynamical Chern-Simons models gives rise to an amplitude that you can imagine is not that large, because also the degree of gravitational circular polarization is between -1 and 1. However, by no means one needs to consider the most standard results, and so in order to see other examples beyond the standard Chern-Simons model, we include this enhancement factor F. So that's what's represented here. And so let me now talk about 2 models which can give rise to F that are larger. So the sort of first example one can think of is one with a superluminal scalar sound speed. And so the way that this works is that instead of having sort of the interaction between the graviton and the kinetic term of the scalar field just be proportional to a sound speed of unity, you just slap in a vertex interaction that's larger. So initially you had an X that was 1, and now you make it larger, so that's why you're going to get a bigger result. Precisely in the collapse limit, F is proportional to the sound speed to the 8th power. You can sort of maybe see that it should go as to the 8th power as follows. So if each vertex in here pulls down 1 factor of c sub s squared, so you get 2 of those, so that's c sub s to the 4th. The other 4 factors of c sub s come from rescalings of conformal time integrals and from rescalings of actually the primordial scalar power spectrum. So once you count for all of those factors, you get a c sub s to the 8th. But what this means is that a modest amount of superluminality, so if I just have 6, leads to a huge enhancement of your trispectrum, so times amount of 10 to the 6 or so. The other sort of example that we sort of entertained is that of quasi-single field or multi-field inflation. So in this case, we have an additional field, delta sigma, which is heavy, and it has one interaction that sort of mixes the fields, sigma with the inflaton phi. And since it has its own kinetic term, it has its own, therefore, interaction with the graviton that you don't have to add. And what you get is a diagram that sort of looks like follows, where triangles tells you go from an inflaton to this isocurvature field, and then this axis now represents an interaction of the isocurvature with the graviton. And this isn't the only diagram, but it's one that I'm choosing to show right now. And what essentially people have shown before is that in the collapse limit, there's an enhancement over the original slow roll case because the isocurvature field is not required to obey slow roll restrictions, so its potential can look pretty wacky and large in ways that can lead to large signals. And that if you have the mass of this isocurvature field be obeying the constraint such that it's that of the highlighted piece I'm showing right now, then you can get enhancements of about 10,000 or so. But this is for sufficiently massive particles. You can see that if I took m all the way to 0 via this formula, then I would get something that is 3/2. And as I decrease this mass, I actually get larger and larger enhancements because the isocurvature field exists in the inflating universe for longer. So you can see go the opposite way. If I had an infinitely heavy particle, it wouldn't do anything really for inflation. So a sufficiently light particle will actually lead to a larger enhancement, and what you can show is that it'll lead to a enhancements of like 10 million or so if you have, at most 60 e-folds before the end of the inflation.
And what was the motivation for this? V or nu equals square root of 9/4. What is the reason that needs to be less than 0.5?
Oh no, this was just the regime that was considered in that paper.
Yeah, okay. Then I can believe that the capital F will depend on that thing in some way, just because it's depending on the mass in some way. I mean, yeah, okay, cool.
Yes, exactly. It's all a numerical calculation. This is not anything that is easily seen the behavior. And this function W here is not something you have like a functional form for. That. I mean, you can fit it maybe, but it's not analytically derived.
But in principle, this square root of 9/4 minus m over h squared could have a value bigger than 0.5.
Yes, yeah, 100%. Oh yeah, it can go all the way. So on the right-hand side, I'm saying like if it goes up to 3/2, so it goes as it can be imaginary even. So this is when people talk about like cosmological collider signals, and m over h becomes bigger, then it becomes imaginary, and you get oscillatory features in it. But yeah, for this case, you consider it usually to be real and somewhat heavy, but not too heavy. And if you go all the way light, then you get even larger enhancements. And so what you can sort of conclude from this story is that the trispectra can be large, but this is relative to the standard Chern-Simons gravity case. The next question you may ask is, like even though they can be large as a model sort of example, can we actually observe them? How sensitive are we? It's decently large in that respect. And so let me go through this. So in order to talk both about the parity even and parity odd trispectra at once, I've written here sort of the sensitivity to both and using this Kronecker delta function, which when p is equal to even, you're talking about the even part, and when p equals odd, you're talking about the odd part. So either this left-hand side looks like r, or it looks like pi circ times r. Now, again, due to the constraints on the tensor to the scalar ratio, the sort of maximum value you can imagine this taking is 0.04, which is why this is sort of this fiducial amplitude here. And what this equation is saying is that if I want to see a 3 sigma result, I can achieve that with a enhancement factor of about a million or so if I observe 10 to the 6 linear modes between a minimum wave number of 0.003 inverse megaparsecs to a maximum 0.3 inverse megaparsecs. And that's achievable. And so if I look at the parity odd case, specifically what this is telling me is that f needs to be less than about 4 times 10 to the 9 JeV or so for a 3 sigma signal, assuming Hubble is 10 to the 14 JeV, and so slow world parameter is about 10 to the minus 2.
Can you just remind me, what is the left-hand side of the top equation?
The left-hand side of the top equation is, roughly speaking, the amplitude of the parity even and parity odd parts. So if I take the Kronecker delta function to be even, then this thing in brackets is just equal to 1, and so it's just r. But if it's p is equal to odd, then it's the 1's cancel, and so you have pi circ times r. And so it's either pi circ r or r.
Right. And how does pi circ r times r tell me whether I can measure the signal or not?
Well, so it also depends on f on the right-hand side, but the way that this is written. So I could have written it with f on the left-hand side as well, but essentially what this is saying is that what are the values of r and pi circ needed to get a 3 sigma signal? This is sort of what this equation is telling you. And it's saying that pi circ r needs to be greater than about 0.04.
I see, because little n is the number of sigma of detection.
Of sigma, yes, correct. Little n is the number of signal of detection. The degree of circular polarization is related to the Chern-Simons decay constant. When you take that equation for the parity odd piece to a statement on f, you get the equation at the bottom.
Which specific model are you looking at now? The sound one, or the quasi-single, or just the parameterized?
Yeah, parameterized with this enhancement f. Yeah, just if you throw in a phenomenological f, because while we consider 2 examples only explicitly, if you're considering changes beyond standard Chern-Simons inflation that only involve changes to sort of the internal momentum structure and nothing about the external bits, then it's only going to ever change it by a constant factor f. This is because since you're taking the momentum to 0, any momentum-dependent factors drop out. And it's just a constant factor that you get. Sort of another, if I may, thing is that in the collapse limit, the trispectrum becomes exactly the product of 2 squeezed bispectra. So if you have a tensor scalar bispectra that's squeezed, and you sort of loosely square that, you get a trispectrum in the collapse limit.
I have a really, it feels like a dumb question, but so in your action, you had this additional term that was parameterized a little bit by this little f, and then when you derived your result without the capital F for the amplitude of the signal, it didn't depend on little f.
It does.
Via pi circ.
Yes.
Yeah. Okay. So what's stopping me from changing f to be, I guess, so small so that it's such a big effect? Why is then the final effect constrained to be a maximum amplitude of pi circ being 1? Why is it not getting even bigger and bigger and bigger and bigger? What am I missing here?
So pi circ is defined as the difference between left and right-handed divided by the sum. So by definition,
Sure. So I get that. I get why pi circ has to be between 1 and -1. I just don't understand why this equation is then bounded. Can I not have the amplitude of this potentially parity violating term just be enormous? Like have little f be 10 to the -50. What will happen?
So, okay, so there's a few things to say. So let me first, I guess, clarify just to make sure. So capital F here is going to be something separate. And the only way F enters is through pi circ. So let me first check. Is your question, why does F only enter through pi circ?
So ignoring capital F for now, if I just set little f to be 10 to the -100, is this, like, have I broken something, or is this equation still true? Why is that not blowing up this imaginary piece of the trispectrum?
So, yeah, good question. So there's a few things. So it would, in principle, blow up if you considered F such tiny, because one thing I haven't mentioned here is that I'm considering the regime where essentially there's this parameter mu here, and this is called the chemical potential. That's why it's mu. And I'm taking this to be small because I don't want to introduce a ghost into the theory. If you take F to be too tiny, you'll introduce a ghost. Moreover, you can't take F to be too tiny just from a sort of phenomenological perspective, because getting 10 to the -50 EV F out of like 10 to the 14 Jev physics is rather difficult. I'm not going to say impossible, because maybe one day someone will think of some like really clever idea, but typically, if I'm at 10 GeV scales, I have things that are 10 GeV and above.
Okay, so F has been constrained via some kind of theoretical motivations to not be in a parameter range that would break that equation. I'm happy with that.
If you took it to be smaller, what it'll happen is that you'll have an exponential x increase. And also, one thing that you'll also have to do in such a regime is that you also increase the tensor to the scalar ratio. So the tensor to the scalar ratio also depends on F in such small F values, and so you'll also have to tune other values away. It's a bit more hairy, but for the analysis at hand, there's theoretical motivation to why we don't take it F to be too small.
I think that's actually a very satisfying answer. So essentially, F is treated to be, I guess, sufficiently large so that the amplitude of that new term is sufficiently small that it's not having an impact on the tensor power spectrum that is big enough to be measurable. And therefore, it's not showing up in that final equation beyond the pi circ. Whereas if it got too big, then eventually it would actually affect the tensor power spectrum. And at 10 to the -100, it would be dominating the tensor power spectrum. Okay.
But you could still do this. You could then just lower your other parameters down more. You can make the slower parameter even smaller, and then make Hubble smaller and whatnot. It's phenomenologically viable, but
okay. Well, if you're a theorist and you want to explore that regime where I guess the energy density of inflation is dominated by that term, not some other term, then maybe you'll find interesting phenomenology. Don't forget to cite the cosmology talk, though.
So this tells you how sensitive we are to collapse trispectra, and also to mention when these number of modes are being mentioned, we've taken into account imperfectness in terms of measurements. So number of modes that you have is related to the volume of your observed survey between some minimum and maximum wave number, where the minimum wave number is determined predominantly by the volume of the experiment, and the maximum wave number is determined by the scale of nonlinearity evaluated at the median redshift of your sample. This factor W here is a wedge factor. It is equal to 1 for galaxy surveys, but it is non-zero for 21 centimeter experiments. So 21 centimeter experiments have large foregrounds, and so therefore you need to look outside the beam for the most part to avoid these large foregrounds, and so that cuts out some of your signal. This sort of factor encapsulates that. There's both a linear and nonlinear power spectrum, and so we account for the fact that we have nonlinearities, and nonlinearities don't trace the primordial structure, and so there's a loss of information encoded in this sort of decorrelation function G here, which is evaluated at this median redshift, and the noise is also entering in.
So given that your equation above is just order of magnitude kind of stuff, I guess all you need to know is that this equation at the bottom is valid to within 1, maybe even 2 orders of magnitude to have the above equations be valid. So that seems plausible.
Yeah, so exactly. So we showed for these experiments what the values in precisely even that bottom equation is. So for these 7 experiments of current, future, and upcoming experiments, we calculated what the number of modes was and what values of F they would be sensitive to at 3 sigma. And essentially what we saw is that they all can be sensitive to models that have F of at least 10 to the 6 or so, between 10 to the 5 and 10 to the 6 at 3 sigma. And so, and since those values of F are within the reach of the models, 2 examples I showed before, so you can have detectably large signals from the models I mentioned.
Yeah. Which I guess then aren't the minimal model, but are models that can exist. Okay.
Yes, they are. Yeah, I would say I would be the minimal model. I would not say can give rise to something detectable for a very, very long time. For precisely this slide, the fact that you need f of 10 to the 5.
Because f is 1.
Yes, exactly.
Although I am reminded of the original CMB papers. They calculated the order of magnitude size of the CMB anisotropies and then wrote, therefore it will never be detectable.
True. I could eat my words. I would say the analogy here would be maybe something akin to Maldaceno's consistency relation, where the amplitude of the bispectrum is proportional to the deviation from scale invariance, and so that is of order 10 to the minus 2, and so this is sort of like a result like that, where in the standard model you'd expect almost a no detectable signal, but if you get anything large, you know you're dealing with something weird and funky.
Well, when you say the standard model, you should have no signal. Like, I guess you're saying that...
Standard Chern-Simons. Yes. I thank you.
Should I be worried with values of f this big that these alternative models are actually now starting to affect the tensor to scalar ratio as well? Like, is f still in the kind of subdominant regime for the power spectrum, or is it getting so big that it's not subdominant?
So for the tensor to scalar ratio, if you consider like the superluminous scalar sound speeds, they do change the scaling, but they change actually the primordial scalar power spectrum amplitude, and that's how it changes it. But you can mess around with what values of Hubble is needed and what values of the slow roll parameter are needed. It's all within validity, but the precise values changes. Yeah, I'll say the sort of last bit about sort of baryogenesis and how this all relates to it. And so the way that it sort of goes to it is sort of seen by this Pontryagin density term. Let's go back to it. And I'll emphasize that when we're looking at the Chern-Simons term in inflation, this phi here is just the background inflaton, it is not the perturbations. And this Pontryagin density, it is a topological term, similar to how FF dual is a topological term, so it can be rewritten as a total derivative. Since the inflaton here is only a function of time, then really the only important piece after integrating by parts is the time derivative part. And so if we rewrite this by integration by parts, what you have is effectively is a coupling constant that is this phi dot divided by 4f, which you can rewrite in this term on the right-hand side with a chemical potential mu, which is identified with the term in the square brackets. And this is the chemical potential. Why is it a chemical potential? It's most easily seen via the chiral anomaly. So in standard classical equations of motions, all currents are conserved. That's usually what you have, and so you can't have any production. But if you go to your quantum theory, your axial symmetry is violated by the Pontryagin density. If we focus only on the time component, so the zeroth of this index, any current is the number density, and in particular for the axial current is a difference between the left and right-handed fermion number density. So in this sort of discussion, I'm imagining I also have fermions in my theory. And so this axial current is a difference between those left and right-handed fermions, whatever they may be. Maybe they be neutrinos, maybe there's something BSM, but whatever they may be, I now have something that looks like the time derivative of number density is equal to some source. And so I essentially am producing the difference of left-handed over right-handed fermions. I can also see that why I call this a chemical potential is because if I take this Pontryagin density and I sort of insert the anomaly into it and I canonically normalize my scalar field and whatnot, what I get out at the end is a term that looks like h times mu times the difference of left and right-handed fermions, number density of the left and right-handed fermions. And this is precisely something of the form of a chemical potential. You know, if I have an action and wants to be minimized, and if I have something that is has a difference between two species, I'm going to preferentially bias the production of the species that is going to minimize the action, which is similar to how, like when the Boltzmann equations in chemical equilibrium are.
So the idea here is that this is happening during inflation, that
sort of towards the end.
Okay, when epsilon is starting to get bigger.
Because if you do it too early, you're going to dilute a lot of what you produce.
So it might be happening the whole time, but then we only observably notice what happens right at the end.
Yeah, totally, exactly. I should say this has already been proposed years ago, not by me. This is a known mechanism of producing leptogenesis and thus baryogenesis via some Sphaleron transition at some during the electroweak phase. But so this is sort of a generic prediction of such models, and so as a result, because the chemical potential depends on this Chern-Simons decay constant F, essentially if you're able to probe parity violation, you're able to determine that it's actually a graviton causing the parity violation signature at hand, you can sort of actually be saying you're constraining baryogenesis models. And one other thing about this sort of constraining that I forgot to mention before is that the scales of F that I was talking about a few slides ago are about 10 to the 9 GeV. And something that if you spend time in Chern-Simons gravity theories, the typical scales that are probed by gravitational wave experiments, whether they be due to mergers or due to birefringence from mergers to us, or by looking at the orbits of satellites and whatnot, the types of F that are constrained are of order 10 to the minus 10 eV or so. So by looking at instead at large-scale structure or the CMB or whatever cosmological correlator you are interested in, you're able to be probing Chern-Simons gravity at values of the DCS decay constant that have not been able to be probed by other experiments thus far. So it's also, large-scale structure inflation is very high energy, so you can probe high energy phenomena is really the main thing.
The way you would see Chern-Simons gravity in these other things, is that parity violation again? Or
yeah.
So the gravitational waves that like Lisa is detecting would not satisfy parity is the idea.
Yeah.
To me, the very interesting question, and maybe it's just very difficult to calculate, what is the link between, say, capital F or little f or pi circular and the value of parity violation that, if we assume all systematics are under control, has now been detected in the universe? I guess the reason why this is tricky is they did it in real space, and they were just optimizing for detectability, not optimizing for people with theories being able to calculate how big one should see their effect. Can you do that even in an order of magnitude kind of way? What value of capital F is necessary in order to see the effect that has been seen?
Yeah, so right here, it's a BOSS. So they use BOSS data to do it, and so you need an F value of about 10 to the 2 times 10 to the 7. And so if you have 2 times 10 to the 7 F, that's cool, assuming you have, and that would be for a 3 sigma signal. So that was the one from Oliver. If instead you wanted to deal with, Jamin, Zach's, and Bob's, then you need to scale this by 7/3 and the other one likewise by 7/3.
That's a bit confusing to me, because I thought that the amplitude of their two signals was actually completely consistent with each other. It was just that arguably one side is doing it more optimistic, arguably the other side is doing it more conservative. Like, what you prefer is what you prefer, but potentially they've got the same value of capital F, right? So why what am I missing here?
Well, because one group said it was a 7 sigma signal, and the other one said it was a 3 sigma. So the value of this n right here that goes into this estimate changes. If I ask how big does the amplitude need to be to generate a 3 sigma signal versus how large does an amplitude need to be to generate a 7 sigma signal?
But it might be that they're essentially doing a different value of capital N modes.
Yeah. No, so if you've changed the value of n modes, then that's different. But here it's assuming, if you assume n modes to be the same.
I think that their analysis is going to have a different number of N modes. I think that the more optimistic one of Jim and Zach and Bob probably is including more modes, and the more conservative one of Oliver is probably cutting out some modes. Because from what I understand from talking to both sides, their value of the amplitude is in principle consistent.
Yeah, I agree. I mean, my statement is that if you have the same number of modes and you change it, then that's the 7/3 is what comes in. If you are changing the number of modes, then that's going to let that float in the n mode is going to change by the square root of 7/3.
So I guess the interesting question is exactly, or to within an order of magnitude, what value of n modes did they actually use? Because presumably they didn't do the most value of n modes, because even the more optimistic group was probably also being conservative to some extent. So they might be detecting a bigger value of F. I don't know.
So yeah, I don't know the n modes for the optimistic group. I can say for the more conservative, the n modes here is more representative of that.
I see. Okay, so for Oliver's one, because I guess he was a co-author, as we can see at the bottom of the page, 2 times 10 to the 7. So okay, I guess that means with some of these future ones, the 3 versus 7 sigma might become 100 sigma.
Yes.
All right, so yeah, what's coming next? What should we watch out for? I guess with the baryogenesis side, are there additional free parameters like the coupling strength to the fermions, or is that completely covered by little f?
By little f, it's all produced through little. Yeah, it's there's nothing else you need to add. I mean, you have to add the fermions, but the fermions should be in principle there already in any theory we have. I mean, neutrinos are there. So I guess to sort of highlight what's been done so far, we've shown, like that a massless spin exchange can yield a parity violating scalar trispectrum, that we can look at the scalar trispectrum at very large values of the DCS decay constant, and that we can get direct information about the spin of the exchange particle in the collapse limit of the trispectrum, and that there's some potential new probes of baryogenesis. Now, there's a few things that I think I personally want to do. One is I want to sort of remove this ghost I mentioned sort of passingly earlier, so we can look at smaller values of F. and for a larger range of parameter space. I also want to see how the parity out signal is for all configurations, not just the collapsed. So when you're talking about the regime of Fs that were considered in this paper, we've essentially looked at for all configurations. But once you start to look at different values of F, you start to need to worry more about the ghost, and so you need to remove the ghost first, and then you can start to consider what other shapes are possible. Because even in the parity even case, no one knows what shape maximizes the amplitude of the signal. Just no one knows. So what is actually the shape that leads to largest signal? I showed you how large the collapsed trispectrum is, but there are other shapes maybe that have even larger signals. Where did the trispectrum peak? Same thing. How does it look for in the CMB? You can also ask, I mentioned passingly how gravitational wave experiments look at 10 to the minus 10 eV or 10, much smaller than eV. This sort of probes Chern-Simons gravity at the scales of like 10 to the 9 GeV, 10 to the 5, 10 to the 10 GeV. Is there any type of sort of things you can look at in between those scales for Chern-Simons gravity? And then when you look at sort of baryogenesis, what type of spin 1 baryogenesis can be probed? So there's no reason why you need to consider something like, Chern-Simons gravity. You can consider phi FF dual, as I mentioned before. And so but unlike gravity, you then need to add like a vertex interaction. And so what type of vertex interactions are able to be probed? What shapes are you sensitive to, et cetera, et cetera. And also, besides just, the trispectrum as a way to look at a baryogenesis, are there other CMB and LSS probes of baryogenesis that we can look at?
I guess the other parity violation thing is this birefringence signal, which is measured in the CMB, which, okay, let's just be super optimistic and say both parity violation is real. One would want, ideally, something that is explaining both. And is some inflationary phi FF dual term that's generating the correlation function type of parity violation totally valid as something that then just sort of hangs around and then later on is causing the rotation of the polarized CMB light now? Is that something that sounds plausible? Or
I think the big problem would be the fact that the scales of F involved to make both of them large. I think the cosmic birefringence would require much smaller values of F than is allowed by inflation. But that's just sort of like a naive first pass. By no means is it.
I suppose if we're being the most extreme level of optimism, one could have a F being energy scale dependent or something. I don't know, like a...
So, I mean, you could... The thing that I think that I maybe had in my mind at one point is if maybe somehow you can have, parity violation occur at high energies with one F, but then you have a kinetic mixing term at low energies that somehow reduces the effective scale in some way. I'm saying words only at this point, but I wouldn't be surprised if one can cook up a model to tie the two together, but I don't have something concrete to say immediately.
Yeah, and also if one cooks up the model, how is that better motivated than just having two independent sources of new physics with two different parameters that aren't related at all? I guess it reminds me of some of the models that try to link dark matter and dark energy that, yeah, okay, in principle they're linking them, but in practice it's just two numbers that can be explained independently. Okay, it's still compelling to try. Hello, we recorded that video back in April for various reasons that didn't get it out until now. If you're a fan of parity violation in cosmology, there is the Parity Violation from Home conference running in the last few weeks of October for 2 days each week, Monday, Tuesday each week. If you want to come to that, then there's information about it in the description of the video and the registration page. It's open to all cosmologists and will follow a very similar format to Cosmology from Home. Check that out if you're interested. Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos. Click like to help with YouTube algorithms, both for the channel and for yourself, because YouTube will know to recommend more stuff like this to you. Share the channel with your colleagues. If you have any questions or suggestions, leave a comment. Otherwise, yeah, check out the talk we had with Xiaomin, Zach, and Bob on the possible detection of parity violation in the 4-point function. And thanks, Cyril, for the great talk.
Thank you.